And here we are at Monday part 3, quantum numbers in real life. Where are they? And the answer is, well, everywhere there are waves. So we talked about a couple ones, but so here's a case where you probably don't want to see a wave. This is the Tacoma Narrows Bridge. Google that if you want. And this is, again, a bad instance of a wave. But you can kind of see that this motion is twisting around the center point of the road deck of the bridge. And this is actually just moments before the bridge actually collapsed. And we talked about the other place where you see waves. This is a far less dramatic one, but stringed instruments. All right, so now it turns out that electrons, you might think of them as like little negatively charged particles, but it turns out that they act very, very, very much as if they are waves. And unfortunately, their wave motion is far more complicated than strings, ropes, round rubber mats, the drum skins, or anything else. So just to give you an example, this is not the simplest wave function. So this is, that is used to describe the motion of an electron or the existence of an electron that is constrained to a space the size of an atom. It is the second simplest one. So I think that's going to be the last one that you're going to see. What you do need to know is that these functions that can adequately describe the condition, state, motion, whatever you want to call it, of an electron in an atom needs 4 quantum numbers to describe it. So not 1, not 2, but 4. And we have names for them. There is the aforementioned n, but this is a completely different n than the strings. There is L, and it's usually a script L, M sub L, and M sub S. So this graphic here, which is from the group activity that I would have normally given you, shows you pictures of electrons with various sets of quantum numbers to describe them, N, L, and M sub L. Only talking about 3 of them right now. And what I want you to do is look at these pictures and try to figure out what physical property of that electron does one particular quantum number tell you. And in particular, of the 3, N, L, and M sub L, one of them will tell you exclusively the shape, one of them will tell you the size of an electron with that quantum number, and one of them will tell you the spatial orientation. Now keep in mind that any one electron could adopt any of these states. It could look like this one, or it could look like this one. These are all possibilities. And under each cartoon, I've got the 3 quantum numbers that would describe an electron that looks like that, or that looks like this. So look at, between these 2 sets of pictures, look at what changes and what stays the same. And so first off, tell me which one describes the shape. All right, so for this one, you want to look at, so these all have the same shape, and they are different from these that have the same shape. And what is exclusively different? So these all seem to have an L equal to 0, and they are all the same shape. These all have L equal to 1. They are within themselves the same shape, but are different from this shape. So that points to L being the determiner of what the shape is. So the next task was to identify the quantum number that tells you the size. Well, these are all the same size, so this might not be particularly instructive, but note that these are all different sizes. And in this case, for these 3, there is only one quantum number that changes between them, n. So it is 1 here, it is 2 here, it is 3 here. These are all the same, and it is always 2. So those lead you to believe that n is probably the quantum number that determines or tells you, among other things, how big that electron actually is. And finally, spatial orientation. Well, these here are spherical, so spatial orientation doesn't really mean much for these guys. But for electrons that are like these, you can see that they are aligned among, in this case, the XYZ axes. And for these three, n is the same, L is the same, but m sub L is different, -1, +1, and 0. And that would lead me to believe that m sub L will tell you the spatial orientation of a particular electron. All right. So these are just some of the things that just knowing a quantum number about an electron can tell you. That how big a volume of space it is occupying and what the shape of that volume of space happens to be. Now, okay, so apparently I lied. I was going to show you this equation one more time. So this is an example of a wave function, and I've actually condensed this one a bit. These are usually given by what's referred to as the pitchfork thing. This is a lowercase psi, or the trident. And this function, it is a very important theory of wave mechanics, is that if you know the wave function of a particular thing, that function will allow you to describe or predict any dynamic quantity about that thing, in this case our electron, given enough math workup. The simplest example of that is that you can use this wave function to determine the probability of finding an electron at a particular point in space. And all you need to do for that is plug in x, y, z coordinates in space and square it. And that result, so the wave function squared, will tell you the probability of finding that type of an electron at position, at a position in space given by those x, y, z coordinates. So this is why these are often also called probability densities. Notice how that we are not talking about the actual position of an electron, only the probability of finding it at a particular point in space. This is an aspect of electrons being very wave-like, that they sort of exist everywhere and nowhere at the same time. So you have a 80% chance of finding it at this one spot in space. So another thing that you can do, and I'm not even going to show you this, is you can apply an operator to this function. Now, like I said before, these wave functions properly have 4 quantum numbers in it: n, L, m sub L, and m sub s. And you can apply operators to functions, and an operator is just a rule that changes a function into another one. So for example, derivatives and integrals are actually examples of operators. Now this Hamiltonian operator is a complicated one. It involves taking a second derivative, squaring a couple things, and multiplying by some constants. But that operation, and trust me, you don't want to actually see it done, operated on it gives you the original function back and the energy. So it's the original function multiplied by the energy. And one of the interesting things that comes out of this, it is interesting and also very important, is that the energy depends on only 2 of the 4 quantum numbers. The energy depends only on n and only on L. The parts of the function that end up with, that depend on m sub L and m sub s actually don't, end up sort of dropping out of this treatment. So the energy depends only on n and L, and that's kind of important. Now, there are some other, because of the pretty intense math that this entails, there are actually some restrictions on the values that these quantum numbers can achieve. Just like when we're talking about our string, the quantum number had to be, integer that was at least greater than 1. And this is pretty complicated. It turns out that the restrictions on the quantum numbers are sort of interrelated. So I'm kind of going to go through them and then do an example. So the first quantum number, n, can be any positive integer from 1 all the way up to infinity. N is often referred to as the principal quantum number. The next one is L. And allowed values of L are any integer from 0 all the way up to n minus 1. So the possible values of L depend on where you started with n. And likewise, possible values, this is often referred to as the angular momentum quantum number or the azimuthal quantum number. And I think azimuthal is just a much better word to say, and I cannot wait to see what the captioning gives me for that. Next one, m sub L. Like before, depends on L. And the allowed values of m sub L are all of the integers between negative L and positive L, including 0. This is referred to as the magnetic quantum number. And last but not least, m sub S. That is the simplest one. It only has two possible values that are equal and opposite in magnitude. Equal in magnitude, opposite in sign. And normally we just have it as minus 1/2 or plus 1/2. Sometimes we just even have an up arrow and a down arrow. All right. So these are all possibilities. And each one of these together, these four of them, describe what we call the state of an electron or the condition of an electron. And any one electron can adopt a lot of different states. Let's see how many. All right, m sub S is the spin quantum number. That's what the S stands for.